Hello and welcome. Today is Thursday, April 16th. So another round of finals review. Today's finals review number 5. We'll focus on work, energy, power. Tomorrow we'll do momentum and collisions and impact forces, etc. And then we have rotational dynamics on Monday, and that should complete the whole series. Afterwards, we will do various things, more on your part. So expect to do a few more quizzes. 8 and is here, says hi, Mr. Z. Hello, 8 and. I forgot who you were. Yeah, so expect more quizzes starting next week. So small little quizzes here and there to keep you fresh and up to date. So as you can see, based on the calendar, the week of the 20th, 27th, and then May 4th, you have 3 weeks of time to review, and then your test is on the 14th, so technically 3.5 weeks. Okay, I forgot to upload the test corrections. Excellent. Good job, Aiden. Yeah, I'm getting lots of emails about spring break homework now, after I've graded it, after people have found out that it's that I made it extra credit. They're like, oh shoot, I should have done it. Most of you have, most of you did your work, so that's good. You have to stay on task. It's not over. We still have goals to accomplish, so make sure you do. Our assignments are far and few. We're done with mastering physics. There's no more mastering physics, and then these last few quizzes, your final test, and all that stuff, and whatever project we do at the end will be it. All right, so let's go and title our notes: Work, Energy, Power, WEP. Work, energy, power. Recall that work is the integral of f dx. Whoops. We can write it as dot f d cosine theta, where the force and the displacement are vectors, and we have to make sure that they are in the same axis. Otherwise, if you have a force that is 90 degrees, so for example, let's say you have a normal force that is up. Of course, you can have an applied force, and the applied force has components. FAY and FAX, fax and fay. And so if you're on the ground, and assuming that FAY is less than mg, the weight of the object, so you're not pulling it up into the sky, assuming all that, then the block is only moving to the right. Displacement d is to the right, and if that's the case, then the work done by, I forgot the n. The normal force, the work done by the normal force is 0. That's because it would be the normal force times d times cosine of 90 degrees, and that gives you 0. Right, and similarly, the work done by the y component of your applied force is also 0. The work done by the x component of the applied force would be Fa, whatever you're pulling at, Now FA is a vector, right? So FA points this way at some angle theta. Notice how D is to the right, so the angle between the two forces is theta. So by finding the x component, you are essentially doing the dot product, because once you find the x component of FA is already parallel. So one could say, one could say that this is FA cosine theta, and I'm taking the dot product between FA cosine theta and D, and so you would do FA cosine theta times D times cosine of 0 degrees, 0 degrees, and of course cosine of 0 degrees is 1, and hence when you have vectors that are parallel to each other like fax and D, and you take the dot product of parallel vectors, you get just the magnitude, or the multiplication, the product, because the cosine will give you 1 times D. Okay, so only this thing is doing work. Now, of course, if there's friction, friction would do negative work. Friction is that away, and you can see how you would have friction is equal to the force of friction times D times cosine of the angle between D and FF. D is to the right, friction force is to the left, and there's 180 degrees of separation. And this gives you the -1. Now friction force, check your back pockets. The friction force is mu, if it's moving, of course, it would be mu k, kinetic friction coefficient, times the normal force times D. And of course with an F applied, the normal force is not mg, is it? Okay, so make sure you check for those. Do your FPDs. You have two forces in the vertical. Sigma Fy shows you that you have Fay up, normal force up, mg down, and so the normal force is mg minus the y component of the applied force. All right. So work is a scalar quantity, but it could be positive or negative. Scalar, what can be plus or minus. Okay. Recall the work energy theorem tells you that the net work, W net, is equal to, of course it could also be net force times D, but it's equal to delta Ke, the change in kinetic energy. And here we go with all the energy formulas. You should know that the kinetic energy formula is 1/2 mv squared. Okay. Chat, give me all the types of potential energy you have learned thus far. All of them. Give me every single flavor of potential energy. And we got nothing. We got 10 people. For all those kids who are sleeping in, and you need a favor, don't ask me for favors. Right? I'm gonna remember all these students who have come and participated every single day, and who are participating via writing comments on our YouTube video down below, right? So, and everyone else who's like sleeping in and doing nothing, well, sucks for you guys. Bubble Guy says spring potential, gravitational potential, electric potential. Cool. Here's a rotational flavor of kinetic. 1/2I omega squared. So U is the general, or capital U is the is used instead of, you know, PE, potential energy. And of course we have various forms of potential energy. So we got Pegmaga. Ooh, that's my gamer tag, don't use it. Is thermal potential? No, thermal is not potential. To be potential, you have to store the energy. This is energy that is stored. So you have to store it, like in a bank, or better, a field, a conservative field is better than a bank. Or, I don't know. One could argue that a bank is better if you can get some interest. But a conservative field is a field that stores your energy and is able to give it back without any loss, any frictional loss. So Pegmaga, MGH, we have, what else? Gravitational, we have spring potential, PES, of course. PES, or elastic potential energy, 1/2 kx squared. We know more. You guys are not thinking about all of them. Electric potential, okay, fine, PEE. Chat, what is PEE equal to? Well, it's force times distance, so electric force times distance. KQQ over R. Yeah. There's another one that I showed you, one that you'll need next year, and that's the capacitor. 1/2, or if you're taking the AP Physics 2 test, that one kid, whoever you are, 1/2 CV squared, where V is voltage instead of velocity. Is this it? Is this it? Now, question, is it possible to store kinetic energy? Is it possible to store kinetic energy? Can you design an experiment or a device, more like, that can store kinetic energy? So we're kind of breaking the bounds between potential and kinetic right now. The answer is yes, you can. How is it possible that we can store kinetic energy and then use it up? Well, if you have, like, zero drag force, so we have to get rid of all of our friction and drag force. One way to get rid of drag force is to be in space. As you can see, there's no air in space, therefore there's no drag forces in space, right? Unless you think about, like, little particles crashing in or something. But when I say space, I mean literally a vacuum. One could say that planets do not observe such forces because they don't really crash into anything as they're moving around. how deep in space you are. How? What do you mean? How deep in space you are? Hmm. Deeper space has fewer particles, right? Well, these are questions that are very challenging and difficult to answer outright. There are no outright answers because space is very different in different parts depending on what kind of local cluster you're in. So, there could be dark matter in some parts of space. There could be a solar flare just went out and the sun just vomited a bunch of particles, and these particles are moving and crashing and such, or so very complex. But assuming that we are in an area where there's not many particles or there's nothing really, technically there is no such thing as empty space, because all of space has something in it, pretty much, some form of energy or another. But if I have a nice vacuum, what I could do is have like a disk or something that is rotating about its axis. So I'll do some work, of course. I have to do work. Now, how much work do I do? Well, that's going to depend on how much, how quickly or how fast the object is going to rotate, whatever the omega is. So the work I do will be stored in the form of rotational energy, 1/2 I omega squared. And so without anything slowing it down, without any kind of friction, this thing will move and spin forever. And so now this kinetic energy is trapped. This amount of energy, this 1/2 I omega squared worth of energy, is trapped in this spinning disk, right? So we have stored kinetic energy, a kinetic battery. And if I want to use it, what do I do? Well, I can, touch it or something, create heat out of it, or if it was like a gear, somehow, attach masses to it. And now if the mass is moving, we are technically accelerating this extra bit of mass. We have to figure out how to do this without any, without loss of, energy during the impact, of course. But, this is PIC, you're going to lose some sort of energy, but you might get something, right? So anyway, a kinetic battery. We have stored kinetic energy. All right. Now, the other energy that we forgot is the other gravitational potential energy. What is the real pegmega? The real peg. Ooh. The real peg, well, recall that when we did pegmega, we are assuming we are near the surface of the Earth. That's not a very good circle, is it? Let's use ink to shape. That is the worst egg I've ever seen. There we go. We are near the surface of the Earth. Oh, look, if I zoom in, the Earth is flat. Whoa. And when I am near the surface of the Earth, let's say for this patch of the Earth, we have a nice uniform gravitational field. Meg delta. That's cool. No, it's a little bit more complex, Charlene. So let's see if we can derive it. The real pegmega. So anyway, and because we have a uniform gravitational field, we can say that the energy is stored is purely based on the height difference, delta H, difference being from whatever H0 you set. Typically we are able to set our initial height, our height 0, to be on the ground. and then we measure anything above it as positive height, right? And so we say that the amount of energy that is stored is equal to the weight of the object times this height differential from 0. Okay. However, we know that if we leave the surface, g is not constant. If we are further out, like over here, g is actually a function of the radius, the distance. I'll call it r star, so it's similar to, so there's some carryover from yesterday. So g star is capital G, mass of the planet, divided by r star squared. Okay, and so notice how the higher I go, of course, now if I look at it from the Peg-Magat model, in the Peg-Magat model, m times g times h, the higher I go, I'm supposed to get more energy, right? The higher the height, more the energy. But what happens to gravity? What happens to gravity? The further away you are from the center, the weaker the gravity. As distance goes up, g goes down, h goes up. Okay, so is my gravitational potential energy increasing as I go higher, or is it decreasing because gravity is weaker? Ooh. Chat, what is going on? Well, one of them is going to win out. For calculus students, you know this as L'Hôpital's rule, or I should say L'Hôpital, the hospital. It decreases, I think. Use your La Hospital and figure out which one's going to win. The rate of change of height or the rate of change of gravity. Well, you can see how height is linearly increasing, and gravity is exponentially decreasing. So it looks like we are, if I am infinitely far away, or very far away, there's no infinity really. So here's Earth, or here's the planet, and now we are very, very far away, and we're all the way out here. Okay, is my Peg-Magat infinity or 0? Ooh, should we do a poll? All right. I'm not very quick with polls. That is the problem. Here, let's do a quick poll. Oops. Oh, I forgot to close yesterday's poll. Okay, ignore the following message. Edit. Infinity or 0? So what you want to do is type I and F for infinity, or 0 for 0. Ooh. All right. So you do exclamation mark vote inf if you think it's infinity, or 0. Actually, there's a space between. There's like a space here between the vote and what you're actually saying. No, Mohammed, no. You gotta type exclamation point and then vote, V-O-T-E, and then put a little space and then type in what you're voting. There you go. There you go. Now you did it. All right, so now that I know, I have to remember to close the poll. There you go, it's working, yay, 100%, whoa, we're so good. Yeah, it looks like at infinite distance we have 0 energy. 0 joules, OJ, orange juice. Thank you. Hey, it's Megan. Where does the energy go? Well, it's not that the energy is lost. It's that we started with nothing. So at infinite distance is our 0 point. We're actually shifting, what we're doing is we are shifting our height 0. So imagine, instead of height 0 being at the surface of our planet, height 0 is all the way out here at infinite distance away. And so if you are closer into the Earth, then you're actually at negative height. Similar to things we've talked about before. Remember how if you have a table and you have an object on the table, and the table is h high off the ground. Oh, it's my pi table. Get it? Pi table. My pi table here. So this object that is off the ground relative to the ground, ground, okay, peg is equal to mgh, right? But relative to the table, tableau, peg is 0. Okay, and if I had object B here, or object 2, for number 2, relative to the ground, the gravitational potential energy is 0, but relative to the table now, object 2 has negative energy. Whoa. Well, it's not that it has negative energy, there's no such thing as negative energy, but it is relative, meaning relative to the table you have less energy. That's why it's negative. So the negative sign means that you have less than your maximum, and we're saying that the maximum energy is 0 energy. You come from nothing, right? And so by bringing this object in, you become more and more negative. And being on the surface, you have some sort of negative peg. Okay, so why is this important? Well, this now works with all of our models. Okay, so imagine having mass m. Now we're going to look at it from a force perspective. Mass m and little m here. Okay, you are bringing these two masses closer together, right? Question: are you doing positive work to bring it closer, or are you doing negative work to bring it closer? Positive work or negative work? Okay. Well, there's only one force between them, and that's the gravitational force. And the gravitational force is gm over r squared, the center to center distance. Okay. And naturally they attract each other. So by bringing it in, you're actually doing negative work. You're doing negative work. You can imagine that the gravitational force is actually a spring, an imaginary spring, and it takes work, it takes positive work to stretch the spring out. So having the masses further apart actually takes positive work, and bringing it in is the same as allowing the spring to decompress, or sorry, I shouldn't say decompress, to go back to its natural length, go back to equilibrium. That's what I wanted to say. So if you're allowing the spring to just collapse back into its natural length, then you're doing negative work, right? Stretching the spring would take positive work. You're storing some energy into the spring energy, or the spring itself. In this case, the spring is the gravitational field. So stretching the two masses out stores energy into the gravitational field, and then allowing it to fall back down means you're doing negative work. Similarly, right, if we go back to our Earth surface gravity model, right, if you recall how I explained gravity is like a little spring attached to the ground, and if you go higher and higher, you're stretching the spring, and when you let go, the spring collapses, and then you accelerate, and kablamo, your peg maga turns into KE. So same thing is happening here. By allowing it, we are losing our potential energy and gaining kinetic. We're gonna so to bring it closer means to do negative work. Okay, and thus we have the energy formula similar to how we did the electric potential energy formula. The gravitational potential energy, UG, is equal to negative G m1 m2 over single r. So you can see how it's essentially kind of like force times distance, but not quite. It comes from taking the integral. Calculus BC students, you can just take the integral. What's the integral of 1 over r squared dr? Actually, Calc AB students, you should be able to do this too. It could be on your AP test, who knows. What's the integral of 1 over r squared? The antiderivative. Clock is ticking. Well, it's negative 1 over r. Or this is r to the negative 2. And the formula is n to the x n. Oops, I should do x. X to the n plus 1 over n plus 1. Bubble guy. You'll get there next year, bubble guy. Actually, you'll at least do derivatives pretty soon, right? In your math analysis, honors math analysis. You'll do derivatives pretty soon. All right, so here we have our formula for UG, the real peg maga. Excuse me. And so if you are doing problems that involve objects that are kind of far beyond the surface of your planet, then this is the gravitational potential energy that you want to use. Okay, but if you are doing energy near the surface of the Earth, then stick to the old-fashioned vanilla flavored peg maga. This is the grape flavored peg maga. Right? So based on the separation distance r and the same universal gravitational constant capital G, we have a certain amount of energy that is stored in our system. But this energy is negative, a negative amount of joules relative to infinite distance, where we have 0 potential energy. Okay? So if I have like a system of objects, here's a classic physics problem. You guys ready for a classic? Oh, look, it's a triangle. Oh my gosh, PTSD. And it's an isosceles triangle. Oh no, not an isosceles triangle. We'll say that all of these are r far apart. And they're all m's. Okay. And so what is the potential energy of the system? Potential energy of the system. Well, the potential energy of the system is the potential energy between each particle in the system. Okay, there's an interaction between these two, so there's Pegmaga number 1, grape flavored Pegmaga. Here is interaction numero dos, U2, and the last one, U3. So the total must be just U1 plus U2 plus U3. So these could be 3 masses out in space, or three stars without any planets or anything. 3 stars that are in this local star cluster, or I shouldn't say cluster, local, yeah, I guess we can. Miniature, some distant part of the galaxy where there's nothing else around. And these 3 objects have a certain amount of potential energy associated with it based on its current position, current distance from each other. Energy is scalar, so you can always just add them. Since energy is a scalar, we'll just add everything up. So this is negative gm times m over r minus g times m over r minus g times m over r. Well, we get negative 3 g m squared over r. So that's the energy of our system. It's a negative amount of joules. Okay. All right. Now what? Okay, so it looks like if I have a planet and an object, and I bring this object to the surface of the planet, so now this object could represent just you standing on the surface of the planet, right? It seems that you, by standing on the surface of the planet, have a certain amount of negative potential. Ah, great. So you're all worth negative energy. How much negative energy do you have by standing on this surface of your planet here, planet Earth? This is UM. Alright. Well, the amount of energy that you have, your potential, well, we'll call it UG. Your potential is negative. Negative capital G mass of the Earth times your mass divided by how far you are. So you are roughly radius of the Earth away. Right. It's technically from center to center, but your tiny little radius is negligible in comparison to the Earth's radius. Okay, so you have negative energy. You can call this the binding energy. And this binding energy is another way of saying that all objects are bound to the surface, or the surface of the planet, because they have negative potential. Clearly, if you have negative potential energy, you're unlikely to accelerate or move upwards. Right? On its own, naturally, it's unlikely to go. You can think of it as in a skateboard half pipe, or whatever they are called. Of course, when you're up here, okay, you have relative to the bottom of this skateboard half pipe, relative to the bottom, you have potential energy, and therefore you have positive potential energy relative to the bottom, and naturally you can go further down, right? If you ever hit rock bottom, you can always keep digging, it seems. So naturally you can fall downwards, but once you're over here, unless you have kinetic energy, if you are already here and you don't have kinetic energy, then naturally you will not go up. Now, if we extend this out, if we are below the surface, then we can definitely not go up with whatever negative potential we have. Right? So if we have negative potential by being on the surface, that means naturally we can't lift off of the surface. We're going to need some sort of kinetic energy to lift off. And so we start to accelerate. We start going faster and faster, kind of like Sonic the Hedgehog. Whoa, we'll run around, run around, run around. And it seems like if I can accelerate fast enough to where my velocity gives me an equal amount of kinetic energy. So we'll take the absolute value of our UG. Okay, the amount that I'm at a deficit, since I'm starting with negative energy, negative potential, okay, I will accelerate this object such that my kinetic energy is equal to this deficit. And so by giving this deficit back, we now reach zero energy, zero total energy, right? So our total would be UG, the negative amount that we have, plus this new kinetic energy. And so this new kinetic energy will be the absolute value of whatever deficit I'm at. And by reaching zero, interesting things happen. And so as you go faster and faster, this G, mass of the Earth, times your mass divided by radius of the Earth. Let's write it in the general form. So we'll just write this as m1, m2, and then we'll just call this r. So here's our general equation. So here's our UG for any planet. It doesn't have to be Earth. And if my UG is equal to my kinetic energy, we have kind of given back our deficit. Whoops, 1/2 mv squared. And this allows us to figure out how quickly we need to move to give back the deficit, the lost, or the negative energy that I'm starting with. Well, V is equal to the square root of, if I multiply by 2, get rid of the m's, this m and this m. Remember, this is the m that is moving, so, which is also this m. That's the one that's moving. Whereas m1 is the stationary planet. G, m, we can call it m central. M central divided by how far away you are from the central mass. Times 2. We forgot this half here, so 2. Whoa, this looks similar to something, right? Maybe I should split this up, shall we? If I said V is, if I split the radical to square root 2 and square root G m central over R, what do you see? Chat. Oh, do you recognize any of this? Root 2g8, close. Ignore the root 2 part. Focus on this. What do you see? I mean, we literally did it yesterday. So this is Vorb. Yeah, it's Rudker. And the orbital velocity formula. But now we're going faster than the orbital velocity formula, right? How much faster? Well, we're going rad 2 times faster. Oh, Emma says exit velocity. Very good. So when you go faster, recall that it turns elliptical. But if you go fast enough, you break that ellipses and actually escape the gravitational pull altogether. So this is the escape velocity formula, VESC. And essentially, if you go rad 2 times faster than vorb, instead of going in elliptical orbits, you're just slingshot away. That's because you're going so fast that that you're so far apart. Remember, as the distance between the planet and the object increases, the force of gravity decreases, right? Force of gravity is gm m2 over r squared. So and it falls off as r squared. So the further you are, the even weaker the force becomes. And so gravity becomes too weak to pull you back down. And so you just keep going away forever. Right? So by giving back the deficit, the negative amount of joules, we are able to leave the pull of gravity. All right. Anyway, this is unlikely to be on the AP test. This is more like AP Physics C stuff in gravitation. But you should know at least UG. You should know UG, and then perhaps next year or after watching Interstellar or something, we can talk about black holes and stuff. Right? So, or actually, we do that in APC, I guess. We talk about weird black hole stuff in APC. Consider taking AP Physics C next year to learn more about space. Oh, did you know I was invited to do a viewing party by Twitch, so I can actually play movies and show it off on my stream. So I can actually show you like Interstellar now, or other movies if we watch other stuff. Let's do a question that may be much similar to AP style. Let's see. Here's one by the College Board. It says a single. Oh, whoops. Here we go. To enable editing. All right. A single roller coaster car initially at rest at position x0 or x0 at the top of the first hill of a track is at rest. The track consists of 2 hills and a horizontal section. So we're on a roller coaster where we are now, even though the graph looks like a roller coaster itself, the graph is not the roller coaster. The graph says forward force on the y-axis and position on the x-axis. So the graph, although it looks like a roller coaster, has force and x. Right, it starts from 0, it goes like this, it does some weird thing, and then it goes up again, and then it stays horizontal, so something like this. So the graph doesn't technically represent what the car is doing. The car starts from top of the hill, top of the first hill. And we know that the car is going downhill. How do I know that? Well, the forward force is positive in the first section. Okay? And so because it's positive, that means we are going downhill, we're doing positive work. Positive work means we are gaining kinetic energy because of the work energy theorem. Work is equal to delta KE. So when a roller coaster car goes downhill, we are gaining kinetic energy. So the origin, which is 0 force, is actually at the top of the first hill. And then we go downhill. And we reach 0 force when we are at the bottom of the first hill. Okay. Now we have negative force. Whoa, negative force. Negative force would mean that I am slowing down. So when do you slow down? Well, you slow down when you're going uphill, right? And it looks like it's symmetric. The graph is symmetric, so we can discuss, like, how high do you go? Do you get back the original? Do you lose any energy? Blah blah blah. But let's just say that it goes back up because it's nice and symmetric. At what point do we hit the top of the second hill? Well, we hit the top of the second hill when we've slowed down all the way. When we hit the 0 again. And then we have positive force. Positive force. Well, let's use a different color. Blue. Positive force. This positive force section would mean I'm gaining kinetic energy again. So woo, down the hill again. And then we stay horizontal. And here's our horizontal part. So even though the graph looks like a roller coaster, that's not where the roller coaster is. The actual displacement graph, that's what the roller coaster is, the displacement graph. Sorry, I should say position graph. This is like more of a two-dimensional position graph because it's giving you height and displacement in the x-axis. A parametric 2D XY graph. We have parameterized it by time. Oh. I wonder if our multivariable kids are here. Probably not. So let's go back to the actual question. We just talked about the graph and all that. What does the actual question say? Well, okay. The track consists of 2 hills and a horizontal section. The horizontal section of the track starts at x equal to 130 meters. When the car is released from rest, the car rolls without friction from position x0 to position x150, 150 being the end of the graph. The graph shows the net force on the car at various positions on the track where positive values of force represent forward force. At which position between 0 and 80 is the car moving the fastest? Explain your answer. All right, so let's go back and talk about graphs because, graphs are important. They come up all the time. If you have a force and displacement graph, F and X. Okay, F and X. Well, F could be, it doesn't have to be a straight line. What if it was weird? And I take the area under the curve, aka the integral. What do we get? And the area under the curve is work. Right? You can see how the width of this rectangle would be some sort of x, right? The height of this rectangle would be some sort of f. And what's force times distance or displacement? Well, force times displacement is work, so that's why. Right. So let's see if we can answer this now. At which position between 0 and 80 is the car moving the fastest? So we have to do a bunch of positive work to get it to accelerate. We start from 0 meters per second because we're starting from rest. So at the top of the hill, we're at 0. And then we do positive work. But after this point here, what point is this? When does it turn negative? Well, this is 50. And how many blocks is there? 1, 2, 3, 4, 5. Okay, so it's going up by 5s, right? 5, 10, 15, 20, 25, and then all the way to 50. So this is 45. At 45, we hit 0 force. And then after 45, our force becomes negative. So if our force is negative, we're doing negative work. You can see how the area under the curve is now negative. We have negative area. So let's go back to our graph. So here's our graph. Only this portion here is the positive area, and positive area means positive work. Pink. This pink part, which is negative area, the negative area would be negative work, and this would slow us down. So we reach maximum when we're done doing positive work, and we are done doing positive work at this point here at 45 meters. Between which two track positions? So now, if this was on the AP test, you would also have to explain your answer, right? So how do we explain our answer? Well, basically, you would have to say things like the area under the curve in a force displacement graph gives us the work done on the object, the net work done on the object. And using the work energy formula, W equal to delta KE, we can see that the positive area would do positive work, giving us more kinetic energy. And from 0 to 45, the force is positive, which means from 0 to 45, positive work is being done, accelerating the cart. Whereas values after 45 meters always have the counter argument. When you write an essay, even in your AP Lane class, when you write an essay, try to have a counter argument paragraph before your conclusion. This will bolster your persuasive essays. Anticipate what the counter argument is, anticipate what the opposite position is, and then disprove them. Cut off their legs before they have a chance to rebuttal. So similarly, the counter argument is talking about all the stuff that is after the 45. Why not 120? Well, because check the question here. It says between 0 and 80. So we have to talk about between 0 and 80. At which position between 0 and 80 is the car moving the fastest? Right? All right. So any point after the 45 has negative force, which would do negative work, which would slow us down. Okay. Yeah, so the question is only between 0 and 80. Between which two track positions does the car travel uphill? Explain your answer. Oh, we kind of already went over this when we were trying to model the roller coaster itself, but now you have to explain it. Between which two track positions does the car travel uphill? So here is the graph, right? And you are asked between, now there's no bounds, it's 1 to 50. Between which two track positions does the car travel uphill? If you know the answer in the comments below. We got a couple of comments yesterday. I was excited. Yay, it's working. Some of you got some interesting stuff talking about how we have to ignore some forces, orbits are not elliptical, blah blah blah. So that was good. So let's go and see if you can answer this one, part B, and then we'll talk about it tomorrow. Between which two points, between which two track positions does the car travel uphill? Or you could just rewind the video. Thank you for tuning in. I'll see you next time.